Even from visual inspection, it's obvious that this block will need a rebore. Here the amount of wear is checked to see whether it will clean up at the first oversize or not. It's a good idea to make a list of all the main components and the dimension of the various working surfaces. When the block has been proved sound, take a look at things like the cam bearings and cam follower bores. These can usually be checked and verified for size by installing an as-new part into them to check for play. Fortunately, most of these surfaces don't wear appreciably. Though this cam is in good condition, we will be replacing it for a high-performance one. Even before measuring the crank journals, visual inspection and the fingernail test can establish if a regrind is required. This particular crank had some journals tram-lined. This is a typical symptom of irregular oil changes or lack of adequate cleanliness at the time of the original build. Inspect the distributor drive gear for wear on bearing and gear surfaces, plus any sign of bell mouthing of the slot in the flange end. Normally this cam gear is likely to have worn. We will later replace it with a stronger Kent Cams adjustable steel gear. This chain is worn out and should be discarded. As is often the case with older cars, the ring gear on the flywheel has worn and would cause rapid wear on even a new starter motor pinion. Push rods must be checked for straightness. Roll them across a flat surface and look for eccentricity in the shaft section. All bent push rods must be replaced. To minimize transmission problems, the conditions around these two bearings should be fault-free, but especially the drop gear thrust face. If worn, replace the case, as a high output engine could cause failure at this point. Excess wear, as shown here, has rendered this case scrap. For minimal transmission noise, the condition and fit of all the components shown here must be checked and rendered sound, especially the primary gear and its fit on the tail of the crank. From prior driving experience, it was known that the gearbox on our project car was in perfect working order, so outside of a visual check, nothing was done to it, other than to install an anti-surge central oil pickup at a later stage. If your gearbox is at all suspect, refer to your Haynes manual for the complete rebuilding procedure. From our strip down, we find that all the parts shown here will need replacing. Our Phase 1 demo car is a relatively new 1000cc model. It's been carefully run in and is now a prime candidate for more power. Paying special attention to safety, drive the car onto ramps and use body jacks to support it. We start the modifications by disconnecting the battery and draining and saving the coolant. This now allows the removal of the heater and top radiator hoses. If so positioned, the coil can now be removed from the head along with the temperature sender lead and the spark plug cables. Now comes the turn of the filter case, followed by the fuel lines. The latter, incidentally, should be plugged to prevent fuel spillage. After prying off the vacuum hose from the carb, disconnect the choke and throttle cables from here and here. Removal of the heater control will now give easier access to the exhaust downpipe clamp, which should now be taken off. Once this has been accomplished, the exhaust system itself can be dropped from under the car. The next item to be removed is the carburetor and manifold assembly. This simply requires the removal of these 6 securing nuts. Because access to the nuts between the intake and exhaust is limited, a specially slimmed down spanner can be of great help. Having removed the carb and manifold assembly, we take a brief moment out of the strip down to deal with some aspects of carburation for our Phase 1 modifications. Vehicles equipped with a single 1.5 SU, especially 1000cc models, can make a lot of extra horsepower still using the original carb. If this is the route chosen, then the carburetor should be at least checked out in those areas known to harbour potential problems. Empty dashpot oil, then take a careful look at the jet. Because spring-loaded needles rub on the jet, the orifice can wear rapidly. Needle wear is far less than the jet, but since the needle will almost certainly be replaced during the tuning procedure, we can leave in whatever is currently installed. Although the original Cooper S was fitted with twin 1.25" SU carbs, a single 1.5" SU fitted to a high-efficiency Janspeed inlet manifold can give similar performance. If the single carb concept is chosen, then the rebuilt carb should be installed on the high-flow water-heated intake manifold, like the Janspeed item shown here. This could also be used on larger capacity engines, as the 1 3/4 SU carb will also fit it. Returning to the strip down sees first the removal of the rocker cover, then the thermostat housing and thermostat. Next, the bypass hose is released, and with that, the rocker shaft assembly and head securing nuts can be undone and removed. The traditional way to do this is to release the nuts working from the middle of the head outwards. After lifting out the rockers, be sure to shake the push rods to allow the followers to drop back into the cam lobes. Since the valve train is to be reused, each part must be returned to the same location, so keep track via the numbered strip of all components. The head can now be lifted from the block, along with the old gasket and the gasket surface cleaned. Back in the body shop, our Project Mini is undergoing some drastic panel surgery. The entire front needed replacing, as did major portions of the floor, sills and rear valance. There are no shortcuts. As you can see, all rust must be removed. A new floor section is used to make good the large section removed. In a similar fashion, new panels are installed where rusted ones have been removed. It's important to position the panels carefully before finally welding in place. In our particular case, this is very critical, as major panels have been replaced and the look of the car must be recreated. Just the rotted door skins can be replaced to save on a new door. Here is a high-mileage crack-free cylinder head. The exhaust valve seats have suffered recession due to unleaded fuel, as shown by the dark band at the top of each seat. The cooler running intake valves don't suffer this problem. During modification, worn or recessed seats can be rectified. You can remove the guides with a punch and hammer, although a hydraulic press does the job shock-free. So far, all we've shown is the basic overhaul procedure of the cylinder head in readiness for modifying it. Now, here's our first move towards performance. We're going to reshape the valves. Many hours on the flow bench testing port configurations have shown that most standard valves are forged for ease of manufacture rather than performance. If performance is the main criteria, the valve shape should be developed on the flow bench. Usually a flatter shape is preferable. From this, a profiling template is made up and used on a copying lathe to transfer the form to the valves. Most A-series heads benefit from bigger valves, but to get the best from any size, the combustion chambers must be reshaped. Tuning BL's A-series engines covers virtually all working combinations. You can mark out the chamber either directly or from a template. Apply marking blue to the areas shown and locate a gasket on 2 dowel pins, then scribe around the bores. This line represents the outer limit to which we can reshape the chamber without compromising head gasket sealing. The next move is to mark out the chamber shape decided upon. For best results, a high-speed grinder driving tungsten carbide cutters or grindstone should be used to cut the head. Hardened steel cutters will not last 2 minutes. Though inexpensive, many will be used, thus making the job so tedious it's unlikely you'll ever want to tackle modifying a cylinder head again. To avoid seat damage, we're using dummy valves located in the chamber. We can now turn our attention to making the ports flow as efficiently as possible. In this shot, we've blued the seat so you can see how the port is being shaped in relation to it. Unfortunately, porting is an area where many head modifiers believe it is polish that produces the desired results. This is not the case. It is shapes developed from the flow bench and dyno that produces results. The polished finish you can see on Janspeed heads is merely a byproduct of quality workmanship. It's important to understand where the port's most inefficient areas are. They're around 1 inch before the valve seat and 1/4 to 3/8 of an inch after the valve seat. The valve itself also constitutes an area of inefficiency, hence the reason for using the shapes developed on the flow bench. A variety of high-performance valves are available. But the valve is only part of the story. Reshaping the throat to obtain good flow basically entails widening it around the valve guide, blending the short side radius and the long side smoothly into the seat area. Although much of the throat can be done at this stage, the final work on the area close to the seat cannot be completed until the seat itself is finished cut. Once the throat has been reshaped, the rest of the port can be blended into it. For the more basic race heads and for road use where exhaust port shape must be compatible with a standard exhaust manifold, Matching the port's exit to the gasket will get the job done. However, it's important to remember that the gasket designer did not use a flow bench to design the gasket aperture. More efficient and exotic port shapes can be produced, but they often require a special Janspeed manifold to complement the port shape. Note that in these views of the completed ports, some of the original casting finish remains. The point here is that shape, not finish, generates airflow. Such minor casting imperfections have no negative effect. If a standard cast iron guide is used, it'll have to be bulleted to reduce its negative effect on flow. With a lathe, this job is quickly done. Here are the shapes before and after on inlet and exhaust. Besides the basic cast iron guides, these bronze guides shown here are an alternative, particularly for using lower octane fuels or high revving engines. Now is the time to begin assembling the cylinder head. With it perfectly clean, brush oil through the guide bores and on the guides prior to installing them in the head. If you're doing the job at home, the valve guide removal tool shown earlier can be used to install the guides. However, they'll all need to be installed to the same depth. When put in our hydraulic press, at Janspeed we use a special fixture which sets all the guides to the correct depth automatically. At home, you'll need to use a rule, or if available, a micrometer, to measure the guide depth and to check that they are all at the correct level as detailed in the Haynes overhaul manual. For the next operation, you'll require some professional services. Look for a reputable machine shop experienced in quality work for high-performance race engines. In this particular instance, we are reclaiming a standard head for a pure restorational project, but the same procedure applies to a modified head. This operation involves cutting the valve seats. So no complications arise with the valve train geometry, cut all valve seats to the same depth within reasonably close limits. At Janspeed we use this special precision machine dedicated solely to cutting valve seats. To cut the seats, a special self-aligning magnetic machining head locates on the plate adjacent to the cylinder head. After cutting each seat, it is checked with engineer's blue. This seat bluing is also used as a provisional reference for the 30-60 degree top and bottom cuts. Bluing is a very useful checking procedure, but it does depend on using just the right amount. Here too much is used, this one is too little, and here is how it should look when done correctly. The same applies to application on the valves. This machining head, which can be used to mount various cutting tools, can be set to cut a precision 45 degree valve seat along with the necessary 30 and 60 top and bottom cuts to obtain the correct geometry for both the valve size involved and the best airflow results. It's critical to ensure a smooth blend from the port into the valve seat. Now we're close to completing the machine work. Now you'll have to calculate how many cc's are required in the head to give the desired compression ratio. Those unfamiliar with ccing calculations and techniques should refer to the cylinder head chapter of Tuning BL's A-series engines. Once you've determined the required cc, make your measurements to see how much has to be machined from the head face. Once machined, the sharp edges are removed from holes around the chambers. This concludes the machine work on the head. We are now at the point where some selective assembly procedures can be started. To check the installed spring height, relatively light springs are needed. Using the components in their intended position on each valve stem, assemble the cotters and spring caps. Next, measure and note distance shown here for each valve. Using this data, shims can now be added to those valves showing too large an installed height. To ensure even spring load, it's necessary to check spring rates to see that they all deliver, within acceptable tolerances, the same performance.